Hi, welcome to the Calculus 1 lecture series. And we are in the unit number 3. We talk about the application of the differentiation. And this topic, the lecture number 24, will be the last topic for this unit. We are going to start to introduce the concept about the antiderivatives. Before this lecture, we talk all about the derivatives, right? So different derivative formulas, applications, and now starting from this point, we are going to take a look at the antiderivative. Then we're going to take a look at what is the integration means here. Okay, now let's go ahead to go to our lecture notes and see what is the the antiderivative means here. Okay, so let's go to our lecture notes. Okay, so the first thing here is let's try to define what is the antiderivative and what are some of the key formulas here. All right, so for the antiderivative, so if we say we use the capital F of x. So if we say f of x is an antiderivative for the function lower f of x. Okay, so what's that mean? That means if you take the derivative of x, it will give you the lower x here. Okay, so this is what we mean the antiderivative. So we will say the f of x, the capital F of x is the antiderivative of, the antiderivative of the lowest case of the f's here. Okay, so if the capital F of x is antiderivative of lowercase, and then we know the f of x going to have these forms here. So the capital F of x, the antiderivatives here will be the c's plus c's here. This is all the antiderivative for what? For the lowercase f of x, right? Why? It's because, we know if you take the derivatives, right? If you take the derivative of the, if you take the derivative of these things here, right? So the constant going to become what? The constant, when you take the derivative, this is going to become 0, and then these ones here become f prime x. Right, so that's why we said, the antiderivative of the lower f of x, it will be the capital F of x plus a constant, because when you take the derivative of constants, it's equal to 0. Okay, now let's take a look at some very common used functions here. Now let's take a look here. The functions here we talked before. Now it's kind of like go backward, right? So this is the antiderivative. Okay, so let's take a look the first ones here. So if we say x to the nth power, okay, here we need to be careful, except n is equal to -1. So we want to find the antiderivative. What is the antiderivatives here? The antiderivative will be x to the n plus 1, the n plus 1, don't forget, plus a constant, c, right? So the reason why this is antiderivative, because if you take the derivative of this one, so you move the n plus 1 to the front, so n plus 1, this n plus 1 cancel, so the top is xn here. Okay, that's what we define the antiderivative. So you can always check. So you can always take the derivative of the antiderivative to see it's going to become your function. So here we say n is not equal to -1. How about if the x to the -1, then what is your antiderivative? So we know the antiderivative will be the natural log x plus c here. And then the next ones here, we say, okay, sine x. we know what is the derivative of sine x. We know it's a cosine, right? So cosine, the derivative is negative sine. So in order to get a sine x, so what is the antiderivative here? It's a negative cosine x plus c. Then the next one here is like a cosine x. So what is the derivative? Will give you the cosine x. It's a sine x plus c. Right. So also we're just going to list like some very commonly used. All right. So like when you come to the calculus 2 class, then we're going to introduce all different type of the skill and the techniques. You can find the antiderivative of some possible very complicated situations here. Okay, so how about the secant square x? So what is the derivative will give you the secant square x? This tangent x plus c. Okay, now the other one we use is frequently is secant x tangent x, right? Now what is the derivative of here? Because it's a secant x plus c. Because if you take the square, if you take the derivative of a secant x, it will give you secant x tangent x. Then the next thing here is EX. Now we say, oh, EX, we really like it because EX, take the derivative, still will be the self. Then also, now we talk about the inverse trick, right? So if your function is 1 over 1 minus x squared, we have 6 inverse, but those two are the most commonly used. So what is this one here? This is the sine arc x plus c here. Then the one last one here, it will be 1 over 1 plus x squared. Like we talked before, we say for this one here, what is this one here? This will be arctangent x plus c, right? So like I said, these few are of the basic fundamental set of the antiderivative. We use it very, very frequently. And of course, when we go to the calculus 2, we're going to take a look how about the function is not simple anymore, right? Now, how do we do that? Okay, so now let's take a look here, right? So now the first one's here, x to the 7. I want to find the antiderivative. That means what take the derivative will be the x to the 7. We said capital F of x equal to what? Is equal to the 7 plus 1, then the x to 7 plus 1. Don't forget the plus c's, right? So this is x to the 8 over 8 plus c. So when you take the derivative of the x to the a's power, you move the a's down. So a and a, this cancel. So we'll give you x7. So you can always check to see your answer is correct or not just by taking the derivative of your capital F of x. Let's see whether you will get your lowercase. Okay, so now for these ones here, this is the antiderivative. This is x to the first power, right? So it will be x to the second power, 1 plus 1 to the 2. And then the EX is by itself, right? So it's still the same. So this will be our antiderivative for the lowercase f of x here. Okay, so now let's take a look at these ones here. So this is f of x, capital F of x. What is the derivative will give you cosine? Sines, right? So the antiderivative of here, this is the sine x minus. What is the derivative will give you secant square? It's a tangent x. That's right. So plus c here. Now this ones here is also basically just apply to the formula. Say, hey, remember what will be the derivative? Will give you square roots of 1 minus. So what is that? We say it's arcsine. That's right. So it's arcsine here. Okay, now let's take a look at these ones here. So this is the f of x equal to x plus x squared negative 2. So this is the first one, x to the first power, right? So it's x to the square, 1 plus 1 is 2. Okay, so in here we'll be very careful here. This is negative 2, right? So this is x to the negative 2. Then don't forget to plus c. And if you like, you can simplify this a little bit. This is 2x squared. So this negative 2, you can write it like this. Then this x to the negative, oh, I'm sorry here. I was not careful here, huh? So you try to rush. That's what's the problem here. So this will be -2 plus 1. So it's what? It's -1. So this is x to the -2 plus 1. So what is -1, right? Plus c. Now, if you want to simplify it a little bit, you can get x squared plus 2, and this is minus. You can move the x to the -1 to here. Don't forget plus c. Okay, so now for this one is 2 to the x, 2 over the x, right? So you can write this as, so you can write this is what is 2 to the what, x to the what, negative 1, right? So you say, oh, x to the -1, I cannot use like the power rule, but x to the -1 is what? So then I can say the antiderivative of 1 over x is what here? It's a natural log x, right? So I can say my capital F of x is here. This is constant, still here. Then the x to the -1 is what? It's natural log x plus c. Okay, so now let's take a look here. So here, this is x to the square, and then this is x to the first power. How about the 4? What is the 4? 4, really, if you want, you can say this is a 4, the x to the 0 powers, right? Okay, so now let's take a look at what is the antiderivative. So capital F of x is here. It will be, this is 12. So this is 2, right? So 2 plus 1 is what? It's 3. Then here, this is x3. Okay, then here, this is plus 8. Then this is 1, right? 1 plus 1 is what? It's 2. Then this is x2. Then plus 4. Here be careful, right? Here is x to the what? 0 power. So what you need to do is here 0 plus 1 is 1 to the x. 0 plus 1 is 1, right? Plus c. So here. Okay, so now you can simplify a little bit. So this will be 4x cubed plus 4x squared plus 4x plus c here. All right. So like I said, you can always take the derivative of the capital F of x to see, whether after you take the derivative is matched the lowercase. Then you will know you got the correct antiderivatives or not. Okay. So the one we said, this one's here, right? So for everything's here, like we said, you always have a C, 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 C's, right? Because this is what we call it the general solutions, right? The general solution of the antiderivative. That means you can have many, because you can change the C. Then because you take the derivative back, the C when you take the derivative will be what? Will be zeros, right? Okay, so now let's say here, so let's the problem number 2, let's say true or false. If the derivative equal, then we say fx, the antiderivative equal to each other. So this is a true or false. This is a what? This is a false here, right? Because we know the general derivative of this one will be what? Will be the f of x plus c, and maybe c1, and this one's here. This will be the gx plus c2 here, right? It doesn't, that doesn't mean the f of x will be equal to the gx because they are off by a constant here. Okay, so now let's take a look at the problem number 3 here. So for the problem number 3, it says here, find the f of x. Okay, then they give you the value. They say, hey, the f2 equal to 3. Then the f derivative is equal to 4x plus 5, right? So I know, okay, so the f prime is 4x plus 5. So I know the f of x, this is the antiderivative, correct? This is the antiderivative for what? For f prime, right? Okay, so now let's see how do we find the antiderivative. This is x to the first power. So remember, what is a 5 here? 5 is x to the 0 powers, right? So we say f of x here, the antiderivative will be equal to 4 times 1 plus 1 is what? Is 2, right? So this is x to the 2 plus 5 times what? 1 to the x. Don't forget it has c. This is our general solutions, right? So this is 2x squared plus 5x plus c. And then now, okay, so and now when they give you a specific values here, okay, so now this one's here, right? So let's say f2 equal to 3. That means if you substitute f2, so that will be equal to what? 2 to the 2, so it's a plus 10 plus c, right? So this is a plus 10 plus c, and let's say it's equal to what? Equal to 3 here. Then you can solve c. So what is the c's here? C will be the negative 15 here, right? So after you find the negative 15, then you substitute here, then you will get your f of x. It will be what? It will be the 2x squared plus 5x minus 15. So for these situations here, right, your c is the your c is defined, it's negative 15. It's not just any like general typical value of the c is defined, okay? So for this defined, then we said this is, we call this the particular, and this is the particular solution of the antiderivative, right? So like a while ago, when we say the plus c, that means a general solution. For the particular solution, this is what we say, okay, for your given number, so I can find the specific the antiderivatives here. Okay, so now number 4. So this is also kind of go back, the backward, like what we learned, right? So let's say a particle moves along a scale with a velocity 3t plus 7. If the particle is S4 on the scales at a time t is 1, find the position functions, right? So if you still remember, right, let's kind of refresh our memory. So like when we, in this unit, we said ST, this is the positions, right? This is a position function. So the VT will be the velocity function. Is you take the derivative of the position function. So this is a velocity function. Then we said acceleration function is what? So it's V take the derivatives, right? So this is acceleration. Right? So the velocity is the derivative of st. So now you can go backward. So I know what st is the what? Is the antiderivative of what? Of the vt's, right? Then the accelerations, right? So then we will say the vt is the antiderivative of what? The VT, so VT is the antiderivative of the ATs here, right? So that's how we go kind of go backward. So now in here, they say that the particle is at 4 when the time equal to 1. I want to find the position function because they given. So here, this is the given is the velocity. I'm looking for the position. So I know the position is the antiderivative of VT, so I need to find the antiderivative. Okay, so VT is the same. This is t to the first, the 7 is x to the 0. So I know the antiderivative formula will be 3 times, this is 1 plus 1 is 2, right? So this will give you what? T to the square, then plus 7. And this 0 plus 1 is 1, and the t to the 1s, right? And then don't forget it's what? Plus c's here. So I have a 3/2 t squared plus 7t plus c. And now I need to find this is very, very specific position function, because it tells us, say, hey, the position is at 4 when the t at 1 is here, right? So what I need to do is here, so I will say, okay, when the t is equal to 1, right? Then you have, this is 3 to the, this is 1 to the square plus 7 times 1, and the plus c. And when t equal to 1, where is the position? The position is equal to what? The position equal to 4, right? Then you can solve the, so you can solve the c's here, right? So this one will be, so the c, if you solve the c, and then you can get a c is -9/2. So finally, my position function will just be 3/2 t squared plus 7t minus 9/2. So this will be my what? This will be my particular solution for my position functions here. Okay, so let's take a look at the last one. This one is also talk about the antiderivative as a particular solution. So let's say the solve dy dx, okay, and equal to x minus secant square. So remember the dy dx is what? Is y primes here, right? So they want us to solve this equation when the y equal to 0, x equal to 0, give the y equal to 0, right? So when x equal to 0, y equal to 0, let's try to solve this. Okay, because dy dx is y prime. So that means I know y is the what? Is the antiderivative of what here? Of the y prime, right? Or the dy dx here. So I need to take the antiderivative of this one, okay? So let's take a look what is this one here. This x is the x to the first power. So the y, right, is equal to the antiderivative. So this will be x. This is 1 plus 1, so it's 2. So this is 1 plus 1, it's 2. And then minus secant square x. So what is the antiderivative of the secant square? Is the tangent x, right? Then don't forget plus c's here. Now, you said that I want to find this particular solution when x equal to 0, y equal to 0. So I plug in the number. So it's 0 is equal to 2 of the 0 minus tangent 0 plus what? Plus c's here, right? So this is 0, this is 0. What is my c? So this is my c's here. So my particular solution is what? My particular is y over x squared over 2 minus tangent x. I don't have c, right? C is 0. So this is my particular solution. Okay, so this section is a very easy section. It's just to give us a kind of the introduction to the integration. We talk about the antiderivatives here, right? So whatever the antiderivative you find, you can check. You can always take the derivatives, right, to see you're getting to the function it's giving you or not. So we have two kinds of antiderivatives, right? Remember? So the one, like in here, I put with all the formula with a C. This is what we call it the general solution of the antiderivative. And then also the last three problems we practiced is like after you solve your antiderivatives, right? Then they will give you some specific value, right? Then you try to solve for the c. So after you solve for the c, then this derivative, this antiderivative, we call it is the particular or specific, right? Antiderivatives here. So also the number 4 is important. We kind of refresh the memory about the position, velocity, and the acceleration, right? So you go backward, right? So we know the VT velocity is the antiderivative of acceleration, and position is the antiderivative of the velocities here. Okay, let's see it. This is a very easy section here, okay? And then we're going to start our new unit about the integrations, okay? Okay, bye. Have a good day here, okay? Bye-bye.